Everyone, I'm Davis Rozier. I am with the engineering section. I work out of the Bay City office, and I am in District 92 covering surface water systems there. I think before we get started here, we're going to start with the first poll question. If Matt, you want to get that going, and then we can move into the presentation.
All right, so this first poll question, we would like to know how many people are viewing this webinar on the device you are logged in with. So you should see that pop up on your screen. And if you are looking to get continuing ed credits, then make sure you select an answer and hit submit. And already up to 93% in the first 30 seconds, so that's fantastic. But it looks like a few more of you are getting a little more acquainted with the poll, and it's working with your computer. Just want to make sure you have an updated system if you're having issues with polling. All right, I'm going to let this go another 10 seconds. And we'll close this out. We're up to 93%. And again, if you do not need continuing ed credits, you can certainly ignore the poll questions. So 95% is where we hit. I'm going to go ahead and end this. And Davis, you can take it away.
All right. So today for session 4, we're going to be covering filtration. Filtration is usually the last treatment process and provides a final polishing of the water. So when we say last portion of that treatment process, that's considering a water treatment process as a multi-barrier treatment process. I think you've already covered some of the earlier steps to that, being coagulation, flocculation, and sedimentation. So the main purpose of filtration is to remove particulate matter, i.e. turbidity. Turbidity is the measure of the light scatter through a water. High turbidity equates to being less clear and low turbidity being more clear. And that's measured in NTUs, which is the nephelometric turbidity unit. Filtration is used to provide an effective barrier to waterborne pathogens. And again, it's part of that multi-barrier water treatment approach. Some important filtration mechanisms. The most important would be adhesion. That is how something sticks to another material. Straining, using the particulate sizes within your media to physically block out particulates. Absorption, which is taking them any sort of particulate into the material itself, and also biological action. You know, sometimes you'll have biofilms forming on the meters in your filters, and that can provide further reduction of organic material. Adhesion and absorption are kind of the most critical to filter media performance and are really what drive our design parameters for filtration. You really want to targeting the most surface area possible for the most effective particulate removal. So this shows here your absorption versus adsorption. So you see with the absorption, the particles are moving into the media. With adsorption, you see they're sticking to the surface there. One important part of filtration is your design, and so there are some really important design considerations to be taken into account. Surface water especially has a lot of variability in your source water. Rivers are more variable, say, than a deep intake lake source. So it's really important to know what raw water quality are coming in. Are there any unusual contaminants present in those waters? So there are certain things you need to consider. What's the turbidity of that incoming water? What's going to be the demand on that filter? Another important design consideration is what kind of pretreatment you have. As we mentioned earlier, there's that multi-barrier approach. So you can have your coagulation, flocculation, sedimentation, But sometimes your plant might have a direct filtration where you're just adding a coagulant, some rapid mix, and then it's going straight into your filter. So that's something to take into consideration. Another important design consideration is the demands on your plant productivity. What is the flow you need to output to support your community on a daily basis? You need to make sure that your filters are designed to handle that flow. What's an acceptable terminal head loss? As you're running your filter, you're going to be building up more and more particulates within it, and that's going to increase your head loss. What's going to be your cutoff point for backwashing? What's your required effluent quality? You at a 1.0 NTU or 0.3 NTU, depending on the community you're serving and the type of treatment you're using. What's your desired filtration rate? Typically for a rapid sand gravity filtration system, you see 2 to 4 gallons per minute per foot squared of surface area on your system. But some places are starting to go and target an even higher filtration rate depending on the technology they're using. And then another important design consideration is your desired length of the filter runs. How long are these filters going to be running before you need to backwash? Usually around 200 hours, but every plant's different. There's going to be a lot of variability. So some more design considerations is your bed depth. How much available head loss do you have through your filter itself? Smaller medias can have higher head loss, so it's important to check into certain design standards. You can check out the 10 state design standards for sizing guidance. Media size and gradation. Media needs to be small enough to capture the size of particulates that need to be removed, but also you need to have them large enough so that you're not restricting your flow through through your filters. Or is it too large and you don't have the footprint available at your plant to fit that media? And that's an important reason why you want to maintain a uniform grain size so that you can adequately design your system to meet those parameters. So some factors influencing your filtration. One of the most consequential impacts on your filtration can be the temperature of the water. Temperature can impact your pre-treatment, and it has a big impact on the viscosity of the water. The less viscous the water is at warmer temperatures, this will impact your filter rates. You'll have a higher filter rate and more frequent backwashing. Filters are designed for specific filtration rates. And again, you want to keep those within keep your filters operating within those design parameters to prevent any short circuiting. Again, the depth, size, and condition of the media. You want to make sure that your depths and uniformity within your media is within your design parameters. This is going to degrade over time. And then again, you can have different types of filters that might have different layers of media in different depths within your filter itself. Another important thing to keep in consideration is your head loss. Again, this can be a sign of your filter clogging up. If you're seeing an increase in head loss through the filter, it could mean there's more going on in there, they're less clean, and there's a higher loading on the filter. So there's a few different types of filters. There are slow sand filters. These are sort of the oldest type of technology. They're a single media filter with just a single sand. Then you have your gravity filters, which there's a couple different types of these. You can have your rapid sand, your multimedia, so you have your anthracite layer, your sand layer, and then a support media or a mixed media, which can have anything ranging from your anthracite sand to an even finer garnet at the lower levels. There's different control rates for these gravity systems. You can have declining head, you can have constant rate. And then you have your pressure systems where you're using an active pumping head system to force your water through the media itself. So first we'll get into a slow sand filter. with a slow sand filter, you typically have a top layer of biologically active media where there's a lot of biofilm forming on your media, usually within the top 18 inches. These filters, again, they're called slow sand for a reason. They have very low filtration rates compared to a pressure system or a gravity rapid sand system, and they require a really large footprint. The cleaning process for a slow sand filter is more involved. You need to scrape off the top layer for offsite cleaning, and then you have to re-add that into the filter. It's also a more susceptible form of filtration to variable water quality and doesn't typically handle a variable water quality as well as a gravity system. So slow sand filtration is known as a declining rate filtration. So as your filters are becoming dirtier, they're filling up with particulates, the flow going through them is going to be reduced. You're not going to have a constant flow. Again, talking about scraping off the top layers, there's a unique word for it, the Schmalzdecke. Again, I'm probably butchering that word terribly, but it's essentially the dirty layer on top with the microbial activity. Washington, D.C. is kind of one of the last large service area systems to implement this type of system. Next, we have a gravity filter system. The filter media is found on the top layers. Let's pull up a laser pointer here. So you have your media up here on the top, and then an underdrain system with a filter to waste, backwash, and effluent. Then you'll have your backwash waste and your backwash troughs, and then all your influent will come in from the top. These can have different types of media and can have different variable layers of media within these. During a backwash period, the media itself is fluidized during the backwash, and this allows for all the captured particulates to be brought up through the top, out the backwash trough, and out into the backwash waste. Often when you are starting back up after a backwash from a system like this, you're going to have a filter to waste option, which is typically around 15 minutes, where you want the media itself to reprime and allow it to begin working adequately again. And in that type of situation, you'll then filter out that or waste out that first 15 minutes of wash on an upstart. So there's different ways to control your flow in a gravity system. It's typically from some type of valving on the effluent. Basically, you can set this to have a specific flow come through. So again, as we said, in a slow sand system, your declining rate. As this media is getting dirtier, more filled with particulates, your rates can decline. So to prevent this, when you're starting off a filter run with a gravity system, you'll probably have this control valve here mostly closed, and then as the media itself is becoming dirtier, you'll open it up to maintain that rate. And you'll typically have a set point along to maintain this. One of the methods for knowing when to backwash is monitoring for the available head loss through your filter media. So that's sort of the difference in pressure from above the media, from your influent point to your effluent point here. And as this media becomes dirtier, you're going to see an increase in your head loss through your filter system. So here's a typical rapid sand filter design. Up here you have your backwash troughs, which during a backwash situation will run all the dirty water with the particulates that's been removed from the fluidized media out the trough and to this gullet into your backwash effluent. Typically with a gravity system, you'll have some form of underdrain, potentially some gravel or support media, and then your filter media. Also, an important part of a gravity filter system are these surface wash units. We mentioned in a slow sand system, you have to scrape off that top layer. And this one, the surface water unit, can sort of circumvent having to scrape that off and replace. It'll help break up any caked particulates on the top during your backwash. And then that'll push it up into the troughs with the rest of the backwash. All right, the last type of filter we have is a pressure filter unit. They are not open to atmosphere. They're fully contained and controlled by a pumping system. These will usually have the lowest footprint of any of the types of filters, but they're also one of the least common in terms of a surface water or large water system. We typically see them being used for iron and manganese removal or radium removal from groundwater systems in Michigan. Here again, you have a picture of one of those small systems here. As you can see, you have two chambers, influent lines going into the top, effluent lines coming out the bottom, and it's all pressure fed. All right, moving on to media parameters. Their media parameters are used to describe or measure the grain size and uniformity of your media itself. The two ones that we are looking for with filter systems are the effective size and the uniformity coefficient. These two parameters sort of are dictating how small the grains of your media are going to be and how uniform they are throughout the filter itself. So you want to have a uniform distribution throughout your media. Along with your bed depth, they also determine how well the filters are going to perform with respect to the quality of water being applied to the bed. So when you're doing your source water determination, when you're looking at designing a filter system, knowing the quality of water coming in is really going to determine what effective size you want for your system. When we talk about effective size, oops, sorry. This is the sieve size that passes 10% of the media. So a sieve is sort of a screen designed for the media to pass through, denoted as E or D10, diameter 10 in millimeters. And then you have your uniformity coefficient. Again, this is the sieve size that 60% of the grains can pass through, divided by your effective size. So your D60 over your D10. A higher uniformity coefficient typically equates to less uniformity throughout your media. You want to target a low coefficient. So that means your 10% media size is a higher quantity of your filter than the 60% size. So you might be asking, what is a sieve analysis? And it's essentially a series of pans having decreasing screen sizes or openings that is used to grade your media. So what's that mean? You're taking a representative sample of your media, you're drying it out, and you're passing it through these sieves. So as you can see, you have your larger sieves at the top down to finer ones, and you're separating out the size of media you have. And this is how you're determining the variation of your D60 to your D10. So your core sample from coarse to fine, and then your sieve size down at the bottom there showing the 10% passing by mass here, and then your 60% further up. Filter media designs are variable. You typically can have your conventional, which is a sand, varying sizes going down to larger at the bottom, with a dual media, an anthracite layer on top with a sand layer on the bottom. You can also have variation of materials. Sometimes people replace anthracite with a granulated activated carbon, and then your mixed media design, which has the anthracite or GAC, the sand, and then an even finer granite or garnet material at the bottom. So gravel at the bottom of your filter media is used to keep your media from washing out through the under drain. It's pretty important to keep a note of. Again, I think that's it. We'll move on. So media, sand media, according to 10 state standards, you want to have a depth of at least 24 inches for sand media. Your effective size, that 10% of sand by weight, of 0.45 to 0.55 millimeters. And again, targeting a uniformity coefficient no greater than 1.6. Next, you have your anthracite media. Again, targeting a depth of at least 24 inches when used alone, an effective size similar to sand, 0.45 to 0.55 millimeters, and a uniformity coefficient less than 1.65. When you're using anthracite in a dual media system, you can actually have a larger effective size in your anthracite because that sand itself below will be targeting those smaller particulates. And then you want to have a uniformity coefficient no greater than 1.85. Third type of media you can be using, as I mentioned, was your granular activated carbon. Again, when used alone, we need a depth of at least 24 inches, similar effective size, 0.45 to 0.55, and a uniformity coefficient of less than 1.65. You might be wondering, why would you use a granular activated carbon media? Well, it has some of the highest surface area of any media in use. So it's great for absorbing organics, and it also has been shown to be an effective treatment for PFAS. Something to take into consideration with this is as you're taking PFAS out of your raw water, it's not something you necessarily want to be backwashing and just putting back out into your system. And after a certain runtime with your filter media, you need to send out that granular activated carbon to be reactivated and to destroy the PFAS itself. Next, we'll get into the media support material. One option for a media support material, again, this is the layer below your filters, your filter media, and is keeping your media from being washed out through the under drain. One option to use is torpedo sand. You want a depth of at least 3 inches when it's underlined by gravel, and you want to have an effective size of 0.8 to 2 millimeters and a uniformity coefficient of less than 1.7. Again, keeping sand and filter media out of your gravel and out of your under drains. Another common media support material used is gravel. This can be of varying sizes. You'll often see gravel of smaller diameter down to larger diameter within a media support system. Again, depending on the size of gravel that you're using, that'll vary the amount of gravel you want by depth. So your smaller gravel sizes, you don't need as much depth. With your larger ones, you want to have a greater depth of gravel. So moving on from there, filter systems have bottom and under drains, and there's a few different options for you can use in your under drain. Again, your under drain purpose is to allow for the treated water to pass out into your clear wells, and also is an important part of your backwashing system. So first type is a lateral pipe system. Basically, you have a header in the center with perforated or with laterals going out with perforated holes or nozzles on those pipes. We got a plan view shown here. They're not the most efficient. You'll see these in some older systems, they can experience higher head loss and will have a less uniform distribution of your backwash. This system also requires a robust gravel and support media system to prevent outwashing of your filter media itself. Next, you have a Wheeler underdrain system. These are pretty common. These are sort of these gridded systems. You can see here a profile view of what that looks like, sort of these conical systems that allow the water to drain through. And then within those conical systems, you have what are known as porcelain thimbles, varying size. And not only do these help support your media, they also help provide a pretty uniform distribution of your backwash flow. Another type is a Leopold vitrified clay block. Again, this is another older system, but essentially what it is a system of flat clay blocks with evenly distributed perforated holes throughout that allow for water to pass through and give an even distribution in your backwash. This is another system you need to have a support media or gravel to keep your filter media from washing out. There's also a sort of updated version of these Leopold underdrains that are engineered. They use a two-lateral system with the primary lateral transporting your backwash quickly, and then the secondary lateral providing the even distribution of your backwash. These engineered systems also can reduce the requirement for gravel and support media. Another type of underdrain system is these nozzle type systems. So they're not called nozzles and strainers. You can even integrate air scouring within these type of systems to introduce air to help further fluidize your media during backwash. Important thing to note is you don't want your air supply lines coming in through the media itself, as that can provide direct paths to short circuit the filtration. And again, these types of systems, you typically don't need as much of your support media or gravel. All right, moving on. There's a couple different ways to control your rate of filtration. First one is a constant rate. So the driving force through your filter, you want to keep at a constant. A valve can be set to automatically operate, as we were talking earlier, in a gravity system based on your targeted flow through the filter or a targeted head loss. Again, at the beginning of your filter run, your filter resistance is very low, and the valve used to add, and a valve is closed partially to add resistance and control the rate. As the filter clogs, the filter resistance will increase, and the rate of filtration can be held constant with that valve opening. Next, you have declining rate filtration. The driving force through the filter is gravity. At the beginning of your filter run, your filter resistance is low, and you're going to have a higher rate of filtration. As the filter's clogging, the filter resistance is going to increase, and your rate of filtration is going to decrease. It's not typically a method you see used as much anymore, especially as most systems aren't using those slow sand filters and can have a little more difficulty in maintaining a constant output of turbidity from your filters. Next, we'll get into backwashing, the cleaning of your media. So there's a couple different things you want to look at to determine whether it's time to backwash. One of the easiest ones to monitor is your head loss. A lot of times you'll set a predetermined level of head loss that will trigger backwashing. And basically this is measuring the reduced pore space. So as your media is getting dirtier, the particulates that you're cleaning out are filling up your pore space and reducing the porosity of your media. Sometimes you can have a target turbidity that will trigger backwash. So say you have a Again, a declining rate filtration. As your filter is becoming dirtier, you might see a turbidity spike near the end of a filter run. Some places will have just a target elapsed time. They'll say we're going to target around 200 hours per filter, and once it's hit that target, we're just going to backwash. And again, trying to maintain a filtration rate. If you have a set design filtration rate, again, that's gallons per minute over foot squared, which is your surface area. Once it's declined to the minimum acceptable flow due to an increased head loss, that will trigger your backwash, again, in a declining rate filter. So how do we do a backwash on a filter system? It's typically done through a pump or a pump system. Some systems have the luxury of having their clear wells at a higher elevation and can use back system pressure to backwash their media. You're typically targeting a backwash rate of 15 gallons per minute per foot squared for around 15 minutes. As you mentioned, the media itself is going to expand to about 30 to 40% of its volume in the summer. That's, again, when your water temperatures are warmer, less viscous, and then expand about 25 to 30% in the winter. So this is sort of a diagram showing what can be done during a backwash. So you're going to close off your effluent valve here. You're going to close off your filter to waste valve, and you're going to open up your backwash valve that, using whatever it may be, your pump system or system pressure, is then going to force the water back through the under drain system and up into your media. It'll then collect here in the troughs, go out into here, and then out your backwash effluent. So backwash rates. Oh, let me get rid of this here. Again, as we mentioned, for a gravity filter, you have about 15 gallons per minute per square foot for not less than 15 minutes. You are typically going to slowly ramp up to that target rate, and then slowly ramp down. Essentially, this is going to prevent blowout of your media out into those backwash troughs and into the effluent. And then as you're ramping down, it allows the media to more evenly settle back down and stratify based on the density of the varying media. So your rise weight is measured in feet per minute, and it can be calculated by multiplying your backwash rate by a conversion factor of 1 cubic foot to 7.48 gallons. So that gives you about 2 cubic feet per minute per square foot, canceling out. It's about 2 feet per minute. That's a good target rise rate for your backwash. When you're backwashing, very important for observation. It's mandatory. You should have an operator there watching the whole process. You don't want any of the backwash bubbling up in a certain area. You want to make sure that there's even distributions. If there's not an even distribution within your backwash, this can be a sign of problems in the media. Again, a reduction in that uniformity coefficient, or potentially an issue within your support media or under drain system. When you're starting a backwash, the water should start off dirty. I mean, you're pushing out all the collected particulates from your filter run time. And then as the backwash runs, the water itself will clear up. You want to avoid losing media. You need to wash down the filter. And then you also need to make sure that your backwash is sufficient to clean the water. Are you running your targeted backwash time and you're still not seeing a reduction in that water clarity? That might mean there's, again, a problem in your under drain system. And then you need to make sure that you're ready to return that filter back into service at the end of your backwash. So again, backwashing alone isn't always enough. showed earlier on one of those diagrams, a surface wash system. These are rotating arms that sweep the surface of the media. It can break up any clogged layers or any cakes that form on top of the media itself. Again, you can also have an air scour with a backwash system through nozzles and the underdrain, further agitating the media and causing increased friction and removal of the particulates that had attached themselves onto your media. So again, here's an example of a surface wash system. Important thing to note when you have a surface wash system is that it requires additional maintenance. These arms themselves can become plugged with media. And again, an important reason to have an operator observing the entire backwash process is to see that these aren't clogged and making sure they're operating as uniformly as possible. So a standard backwashing system in Michigan, the revolving arms are typically operating around 0.5 GPM per square foot. Some older systems can rely on hoses and rakes to manually surface wash their media. And again, the intention of all this is to be breaking up any flock accumulation in the top few inches of your media and breaking up any mud balls you might be encountering. For an air scouring system, the standard design is 3 to 5 cubic feet of air per square foot of filter area. And then this is in conjunction with the backwash with that 8 to 15 GPM per square foot. Some precautions you need to take is you don't want the scour to result in any media loss. You need to check your blower and nozzles for any clogging. And again, the hoses themselves should not pass through the media, as this can short circuit the media itself. And you need to make sure that the hoses in of your air scouring system are designed to be able to handle the weight of the media itself. All right, getting into some troubleshooting for filters. Some common problems you can run into. As we mentioned, you can have mud balls form. If media is inadequately backwashed, thin layers of solids will coat and build up around individual media grains. And during operation, this will increase your pressure loss across the media and further compress these particles, causing them to stick together. Again, we're adding upstream of these coagulants to our water, so it can encourage the formation of these if we're not, again, adequately dosing our coagulation and not adequately backwashing our system. As the mud balls begin to grow, they become heavier and will sink down into the media bed, eventually stopping at the support gravel. Mud balls can also form filter dead zones, which are areas that cannot be effectively backwashed during your backwashing system. Another trouble you can run into without adequate backwashing is bed cracking. This picture itself was taken in here in Michigan, and they had a filter underdrain failure that occurred during backwash. When the filter was placed back into service, the turbidity spikes and it resulted in a bunch of media loss. So essentially the media is coagulating and concentrating on the top of your filter media, forming cracks into the media and allowing short circuiting. All right, other problems you can run into: gravel mounding. If your backwash rate is too high, it can dislodge your support media. If it builds up, this will disrupt the even distribution of your backwash and the overall uniformity coefficient of your filter itself. So short runs between backwashes can result in, or short runs between backwashes. So if you're hitting your target parameter for triggering a backwash, can be a result of inadequate pretreatment, or can result in elevated turbidity events out in your source. And if you're not adjusting your pretreatment adequately. Air binding is another issue you can run into. Essentially, air pockets can form around your media and can fully dislodge the media during backwashing, which will result in media loss. This also prevents the adhesion of particulates to the media itself, which again is reducing the effectiveness of your filter itself. Another thing that can happen is called media attrition. This is typically a result of when calcium is precipitating out of your water due to high alkalinity or other varying parameters within your source water. This can solidify the media, again, reducing the porosity and reducing your adhesion availability of the media itself. So it is important to routinely analyze your media. You need to check the varying layers or types of your media. Again, you want to check if there's any media growth, if there's media wear. I mean, as you are using your media just through the process of filtration, the surface area will be rounded off. The sharp edges will be reduced, and this can reduce the effective size and uniformity coefficient of the media itself. You want to maintain your design minimum depth of your media. Without this, you can end up having faster breakthrough and turbidity spikes in your effluent. Media attrition, you can lose your finer material in a backwash and it will reduce your media depth. So for your media analysis, you want to have an established media depth. So you're essentially creating a datum level elevation above the media, and you want to maintain a consistent depth between that datum level and the top of your media. This is typically done in a grid system throughout checking in 1 foot by 1 foot or 2 foot by 2 foot intervals. You can use strings to sort of lay this out and establish set points or boxes throughout your system. And then again, that datum is the depth from the top of the gravel to the string. And again, this is a good way to check for any sort of mounding or failed under drains. So here's sort of a picture example of how you can determine your media depth. A lot of times this can be done during a backwash to get that rake down in there because the media itself will be fluidized, so it's easier to get in there. You can use a rake, any type of measuring instrument that you can have your set datum on to determine this. Again, determined during your backwash. You can do this during operation. It's just more difficult as that media is more compact. But again, you want to check if there's any variation in your media depth, as you might have mounding in a specific area in your under drain. All right, getting into media growth. So one way to check your media is to get representative core samples. You want to get a sample of the entirety of the depth of your media. You will air dry it in an oven and then weigh it out. Place it in a beaker, treating it with acid, wash with distilled tap water, dry and weigh again. And this is sort of used to determine the difference in weights of calcium carbonate. The acid is used to basically remove any of the calcium carbonate that might have built up on your media. And again, if you're seeing a large difference in your weights pre and post acid wash, then that's a sign that you're having excessive media growth. Media rounding, again, when you have your core sample, you will air dry your media within an oven and then examine it under a microscope. And you really want to have some new media on hand to compare to your in-use media. As you can see in those pictures, an old sand grain on the left, it's been smoothed out. It's much lower surface area than a new sand grain as shown on the right. All right, filter operations. During operation, you want to ensure your filtration rate is matching your design criteria. So you want to make sure that your gallons per minute per square foot is what you are targeting in your design. Also want to ensure that your backwash is to the target rise rate to prevent media loss or settling problems. During operation, you're going to be doing mud ball checks, visual checks during backwash operations, and then again, making sure that the backwash troughs themselves are level. So how can you determine your filtration rate? One way to check on this is to fill your filter box, close the influent valve, and then measure the vertical drop in your water level over time, also known as minutes for test. You can then calculate the volume of water drop, which is your surface area of the filter box times the feet of drop, and then convert to gallons. Then you calculate your gallons per minute per surface area of the filter. So what that looks like, again, you're closing off your influent valve, you have your surface water level, and then you're measuring that drop over a specific amount of time, and then multiplying that by your overall filter surface area. So again, we mentioned 10 states recommends a filtration rate around 2 to 4 gallons per minute per square foot for gravity filters. We can accept higher filtration rates, but it's typically something we would want to see a pilot study ahead of time to really show us that you're going to get appropriate cleaning of the media, and it's not going to result in any excess media loss. So what does particulate removal look like throughout a filter run? So again, when you're starting up media, the media has to ripen. You'll have to have a certain amount of particles begin to attach to your media itself before you're actually going to see a reduction in turbidity. Again, this is when you have your 15-minute, typically a 15-minute optimization period. Plants that have the ability to filter to waste will often just have their filter to waste valve open at that time and won't be adding this ripening period effluent into their clear wells. So then you hit your production period, and this is when it's most important to maintain a constant flow during your production. As the media begins to dirty, then that's when you'll start to see a gradual increase in your effluent turbidity until you hit a breakthrough point. The breakthrough point is once the filter is fully clogged and is really time to backwash. And again, you should be targeting your backwash before the breakthrough begins. So again, you'll have a set effluent turbidity or head loss that'll be at a point before that breakthrough. And again, this is just an example of what it could show, what you've seen or what you could see in a plant in terms of your filter effluent turbidity. You can be checking your SCADA system or whatever way you're monitoring your individual filter effluent to see your typical performance for your filters. Okay, moving on to treatment technique limits. So concentration, sorry, filters can remove turbidity to must remove turbidity to meet current SDWA, Safe Drinking Water Act 399 standards for treatment techniques. So anywhere that's treating surface water, the turbidity needs to be less than 0.3 NTUs in 95% of their samples every month. Sampling can be done more frequently, but should be at regular intervals. Um, Basically, that limit for 0.3 NTU for 95% of samples has been shown to correspond to a significant reduction in waterborne pathogens. Um, Optimized goals target below 0.1 NTU, but again, this is an optimization. Any exceedance of 1 NTU is a public notice and a boil water advisory. Turbidity levels must be collected again at a minimum of every 4 hours, but again, you can do this more frequently if you'd like. So again, we're looking to optimize below a 0.1 NTU. One way to target this is to consider filtering to waste to eliminate any upspike on the startup of a filter. And then a good way to optimize your system is to equip each of your filters with continuous turbidity online monitors. Another way to optimize your system is to monitor your applied turbidity. So what's coming out of your sedimentation basins or out of your flock basin, depending on the type of pretreatment system you have. And this can get you a good idea of how well your filters are treating. So individual filter triggers for online turbidimeters. Turbidimeter levels can be hooked up into your SCADA system. So you would have 2 or more consecutive 15-minute recordings, and you'd want to have automatic triggers for any reading above 1 NTU. You want to have a trigger for readings above 0.5 NTUs after 4 hours of operation for, again, this is for systems greater than 10,000 population only. If you have any reading above 1 NTU 3 months in a row, this is an even greater, this is a violation. And then anything above 2 NTU for 2 months in a row is violation. And I'm a little ahead of schedule, but I think from there, we are going to move on to the problem set next. So if we want to take a 10-minute break here and then meet back at 10:07.
Awesome, Davis. Yeah, sounds great.
All right, I'm gonna bring a clock up here and do the 10-minute timer. So we'll get that rolling so everybody will have an idea when we're going to resume sessions. So all right. All right, we'll see you at 10:07.
All right, that is the end of our 10-minute break. We will get started back up here. I think we're going to start off with a couple polls.
All right, so poll number 2. Let me get this rolling here. You should see a screen that pops up on your screen. Which factor will influence filtration's effectiveness? Well, we got pretty good responses coming in across the board, so we'll share those momentarily. Just want to remind you, if you're looking to get continuing ed credits, you do need to answer the poll questions. And if you're having any difficulty with the poll question, please use the Q&A to let us know that. You can also use the Q&A at any time to submit questions. So if you're looking for any clarification on any of the information that was covered this morning, now would be a great time to submit that. All right, few of you are lingering out there. We're just up to 90%. I'm going to let this run for another 10 seconds. And then we will get back to business. All right, 90% is where we stalled out on this poll. And let me end this poll, and I'm going to share with you the results. I think you're able to see these, Davis. Pressure of water,
Yep.
30%. Okay. Temperature, 54%. Salinity of the water, 6%. And van der Waals force, 3%.
All right, so the correct answer here was the temperature of water. As we mentioned, the temperature of the water impacts the water's viscosity, and that impacts how the water will transport through the filter itself. Looks like the majority of you got it there. The pressure of the water was the second choice for people. Again, the pressure of the water itself in these gravity filtration systems isn't necessarily a impact on the effectiveness. It's a tool for monitoring when it is time to backwash or not.
All right, I'll go ahead and stop sharing that. And I'll let you know when we see your screen.
All right.
All right, we see problem set slide in presentation mode. Take it away.
Okay. All right, we're going to move into everybody's favorite part of the day, some math regarding filtration. We'll get right into it here with problem 1. A filter has sand surface dimensions of 24 feet by 24 feet. How many gallons of water are filtered in one day at a rate of 2 gallons per minute per square foot? And how many filters rated at 2 gallons per minute per square foot are needed to filter 24 million gallons per day? I'm going to give everybody just a couple minutes here to give it a shot on this first problem, and then I will be running it through with you all. Say we'll come back at 10:13 to run through the problem. All right. If everybody could let me know in the chat if that was, or in the Q&A, if that was enough time to sort of give it a shot at these. Maybe in the next ones we can do a little more time. If it's too much, just let me know. But I'm going to switch over here and we will run through the problem. All right. So with this problem, the first half of it, we are looking for how many gallons of water are filtered in one day. So that's going to be our flow. So starting off, what do we know here? We know the filtration rate, and we can determine the surface area rate. So starting off, we know that filtration rate equals flow in gallons per minute over surface area in square feet. So we can start off by calculating our surface area. In the problem we were given that the filter has a sand surface dimension of 24 feet by 24 feet. So we'll do 24 feet by 24 feet, giving us a surface area of 576 square feet. From there, we can use our filtration rate, which was given as 2 gallons per minute per foot squared to manipulate this equation at the top to determine our flow. So our flow is going to equal our filtration rate times our surface area. So for that, we can plug in our 2 gallons per minute times, or gallons, sorry, gallons per minute per foot squared times our 576 square foot surface area. Our units are going to cancel out for the square feet, and we're going to end up with 1,152 gallons per minute. So from there, we want to do a conversion to figure out how many gallons we're going to treat per day. So we have our 1,152 gallons per minute times 60 minutes per 1 hour times 24 hours 1 day. Again, making sure all of our units cross out, so we're getting gallons per day, and that will equate to 1,658,880 gallons per day. So that's the first half of our question. Next, they're asking us how many filters rated at 2 gallons per minute per square foot are needed to filter 24 million gallons per day. So for this, we can use our 24 million gallons per day and our production per day to determine how many filters we need. So we have 24 million gallons in 1 day times 1 million gallons per million gallon, just for the sake of making units easier. And then we know 1 filter can produce 1,658,880 gallons per day. So what do we get here? We get about 14.5 filters. Now you can't have a half filter, so then you round up to a total of 15 filters required. And that'll do it for problem number 1. We will now move on to problem 2. Which is a filter has sand surface dimensions of 24 feet by 24 feet. At a backwash rate of 18 gallons per minute per square foot, how many gallons of wash water are used in a 10-minute backwash? And what is the backwash rate in inches per minute? So we'll give, say, 2-3 minutes on this one as well. And we'll come back at 10:22. All right, we will get back into it here. So for this problem, similar to the last one, we're looking for our flow, but then we're also determining how much flow over a different period of time than a day. So similar to the filter rate, we have our backwash rate is equivalent to flow in gallons per minute over the surface area of the filter in square feet. So again, we can determine our surface area by multiplying 24 feet by 24 feet, giving us 576 square feet. Next, to determine our flow, we're going to multiply the backwash rate by our surface area. So that will be 18 gallons per minute per square foot times 576 square feet, which will give us 10,368 gallons per minute. The question was asking us how many gallons of wash water are used in a 10-minute backwash. So from there, we have our 10,368 gallons per minute times 10 minutes, giving us a total water usage of 103,680 gallons per backwash. Next, it was asking to get the backwash rate in inches per minute. So looking to convert to our rise rate for this backwash. So from there, it's just a unit conversion. So we have our backwash rate in gallons per minute per square foot. So that's our 18, make sure everybody can see that, gallons per minute square foot. And then we need our conversion factors. So in 1 cubic foot of water, we have 7.48 gallons. And then we know, since we want it in inches per minute, we know that there are 12 inches per every 1 foot. So checking on our units, are they gonna cancel out? So we're looking to get inches per minute. Our gallons are gonna cancel out, and then we have cubic feet on the top, square foot on the bottom, times another foot on the bottom. That'll cancel out for our feet. So that'll leave us with 28.9 inches per minute. All right, we'll move on to problem number 3. So for problem number 3, we have a filter bed that is 20 feet by 28 feet, contains 20 inches of sand with the following specifications. The specific gravity is 2.65, the porosity is 40%, 10% of the grains are finer than 0.58 millimeters, 30% of the grains are finer than 0.64 millimeters, 60% of the grains are finer than 0.78 millimeters, 90% of the grains are finer than 0.95 millimeters, and 98% of the grains are finer than 1.01 millimeters. So the first two things we're going to look at here with this problem is, what is the effective size of the sand, and what is the sand uniformity coefficient? So we'll give just a couple minutes on these first two, and then we'll come back and do them together. All right, we'll come back for these first two here. So the first thing they're asking us is what is the effective size of the sand? And if you remember from earlier in the presentation, the effective size for a type of media is your diameter 10, so your D10. And that is whatever size media 10% of the grains are finer than. So we go to what was given in the problem, and our D10 is equivalent to the 0.58 millimeters. The second part, they're asking, what is the sand uniformity coefficient? Again, remembering from earlier, your uniformity coefficient is equal to your D60 over your D10. So again, looking at our information given in the problem, 60% of the grains were finer than 0.78 millimeters, and our D10 was 0.58 millimeters, giving us a uniformity coefficient of 1.3. So moving on, this problem has a couple more parts to it. So the next thing they are going to be asking us is how many tons of dry sand are present in the filter? How many gallons of water does it take to fill the top 12 inches of media? And also, the sand expands 35% at a backwash rate of 12,000 gallons per minute. What is the backwash rate in inches per minute rise above this expanded sand? So we'll give 3 or 4 minutes here on these. We'll come back at 10:34 and we'll run through these ones together. All right, we'll get started on this next set. So starting off, they were asking us how many tons of dry sand are present in the filter media. So the first thing we want to do is figure out the total volume of sand. So this is a rectangular filter. So our volume is going to equal our height by our length by our width. Now we were given that there are 20 inches of sand for our height. So we have 20 inches and then we have to convert to feet, 1 foot per 12 inches. And we're going to multiply that by the width, or by the length, which was 20 feet, and then by the width, which was 28 feet, giving us a total volume of 933 square or cubic feet. Now we were also given in the problem that the porosity of the sand was 40%. So we have to take that into account when determining the volume of just the sand itself. So the volume of the sand is going to equal 1 minus the porosity times the total volume. So essentially what we're doing here is we're removing that porosity, that 40%, which is just the blank space, the gaps between the sand particles. So we can plug in our 1 minus 0.4, the 40%, times our 933 cubic feet, which will give us 560 cubic feet of sand. So from there, we want to know the weight of that sand. How many tons of dry sand are present in the filter? So to get to that, we're going to have to use the specific gravity given in the problem and the known volume of the sand. So starting off with the specific gravity, we know that the sand has 2.65 pounds of sand per cubic feet of sand as a ratio of pounds of water to cubic feet of water. From there, using conversion factor of water, we know that there are 62.4 pounds of water per cubic foot of water. So that's going to give us pounds of sand. From there, we need to know that in 1 ton, there are 2,000 pounds. And we also know that we have 560 cubic feet of sand. So looking at all our units, we want to make sure everything cancels out. We have our cubic feet of water, pounds of water, pounds of water. We have our cubic feet of sand, and then pounds, pounds to get to tons. So we'll end up with 46 tons of sand. All right, moving on to part D. Now we want to know how many gallons of water would it take to fill the top 12 inches of media. So again here, we're looking for the volume. And that will be, getting off the page here, our height by our length by our width. So in this instance, we're looking for the top 12 inches, which we know is 1 foot times our 20-foot length and our 28-foot width, giving us 560 cubic feet. Now in this instance, we're looking for the gallons of water. So we're looking at what's going to fill in between the gaps of that sand. So what's inside the porosity. So our volume of water is going to equal our porosity, gaps between the sand particles, times the volume. So that will equal our 0.4, 40% porosity times 560 cubic feet. And that will give us 224 cubic feet of water. Now it was asking for gallons, so from there we can use our conversion factor of 7.48 gallons per cubic feet to give us a total of 1,675 gallons of water to fill the top 12 inches of our media. On to the last part of the problem, part C, which was asking if the sand expanded 35% at a backwash rate of 12,000 gallons per minute, what is the backwash rate in inches per minute rise above the expanded sand? So what do we know here? We know that our backwash rate in gallons per minute per square foot is equal to our flow in gallons per minute over our surface area in square feet. So we want to determine first our backwash rate based on this. So we have our flow, which is our 12,000 gallons per minute, and we have our surface area. Our surface area is going to equal 20 feet by 28 feet, which will give us 560 square feet. From there, we can determine our backwash rate by having our flow which is 12,000 gallons per minute over 560 square feet, which will give us 21.4 gallons per minute per square foot. Now, what we want to know is our rise above the expanded sand. So this is just a simple unit conversion. So we have our backwash rate, 21.4 gallons per minute square foot times 1 cubic foot per 7.48 gallons of water times 12 inches per foot, giving us a total rise of 34 inches per minute. All right, we'll move on to our next problem. Problem number 4. A filter has a water surface measuring 18 feet by 18 feet. The filter sand dimensions are 18 feet by 15 feet. With the influent valve closed and the effluent valve open, the water surface drops 4 inches in exactly 2 minutes. What is the filtration rate in gallons per minute per square foot? And then, if the plant has 10 filters operating at the same rate, what is the plant's rated capacity? Say we'll give about 6 minutes. This is a little more complex problem here, and then we'll come back and solve this one together. question to see E back up there. So I'll leave that up on the screen. Let me know if you can see that well enough. We'll go back to it before we get started on the next one so I can have a larger view. I just can't have both the problem number 4 and the work from E up at the same time. All right, we'll spend a quick minute here just going over E again real quick. Let me stop sharing and this should be up. So what the question was looking for was the rise above the expanded sand in inches per minute. So essentially what we're looking for was the backwash rate and then converting that to rise rate. The question itself mentioned that the sand expanded 35%. That's a bit of distractor information because it's not really relevant to the problem. That's what we're looking for is a backwash rate and then the conversion. So we figured out our surface area, our flow was given. Our flow of our surface area gave us the backwash rate, 21.4 gallons per minute per square foot. And then from there, we were just converting the gallons per minute per square foot to inches per minute using 7.48 gallons in a cubic foot of water and 12 inches per feet. So I hope that makes sense. All right, moving on to question number 4. What we're looking for here is what is the filtration rate in gallons per minute per square foot? And then if the plant had 10 filters operating, what would be the plant's rated capacity? So first off, we're looking for filtration rate. From earlier, we know our filtration rate is our flow, gallons per minute, over surface area in square feet. Now in this one, we're going to have to calculate our flow. And we know that flow is equal to volume over time. So starting off, we'll get our surface dimensions and our flow. So for our water volume, we need length times width times height. So the filter itself was 18 feet. The water surface itself was 18 feet by 18 feet. So we have 18 feet times 18 feet, and then our height difference was that 4-inch drop. So times 4 inches times 1 foot per 12 inches. And then from there, we convert that directly to gallons of water. As we know, there's 7.48 gallons per cubic feet. So we get foot, foot, foot for cubic feet cancels out, our inches cancel out, and we're left with 808 gallons of water. Now we need to figure out our flow. So our flow, again, is the volume over time. So that will be the 808 gallons over the 2 minutes. Oh, no, it's very straight. Which will give us 404 gallons per minute. From there, we can look at getting our filter rate. So first thing we got to figure out now is the surface area of the filters. So the surface area for the filters is just length by width. And the filter stand dimensions were 18 feet by 15 feet. So that'll give us 270 square feet of surface area for the filters. From there, we can plug that in to our filtration rate equation. So our filtration rate will equal 404 gallons per minute over 270 square feet of surface area. And that will give us 1.5 gallons per minute per square foot for our filtration rate. Moving on to the next part, if the plant has 10 filters operating at the same time, what is the plant's rated capacity in million gallons per day? So our rated capacity is going to equal the number of filters times the flow in million gallons per day. So we know we're going to have 10 filters times our flow, which was 404 gallons per minute. And then we just need to convert to million gallons per day. So 1 million gallon per 1 million gallons. So our units work out nicely. Times 60 minutes in 1 hour times 24 hours per day. So make sure all our units cross out. Gallons, gallons. So for 10 filters at 404 gallons per minute, you end up with 5.82 million gallons per day. All right, we'll move on to our last problem, problem number 5. Pull that up here. All right, problem 5. How many 16-foot square filters are needed to filter 12 million gallons per day at a limiting filtration rate of 2.5 gallons per minute per square feet? Take about 5 minutes here for everybody to work it out on their own, and then we'll run through it together. All right, we'll get into working on this last problem. So we're looking for how many 16 square foot filters are needed to filter 12 million gallons a day at a limiting filtration rate of 2.5 gallons per minute per square foot. So from that last part of problem number 4, we know that a system's rated capacity is equivalent to the number of filters times the flow through one filter in million gallons per day. So first thing we need to do is figure out our flow through a single filter. So our flow through a single filter will equal the filtration rate in gallons per minute per square foot of surface area times the surface area. So for this problem, we know that our filtration rate is that limiting filtration rate of 2.5 gallons per minute per square foot. And then we have a 16-foot square filter. So our surface area is 16 feet by 16 feet, giving us a total flow of 640 gallons per minute. From there, we need to figure out our flow in million gallons per day. So our flow in million gallons per day is going to equal 640 gallons per minute times 1 million gallon per 1,000,000 gallons times 60 minutes for 1 hour times 24 hours per day, giving us a total flow through one filter of 0.922 million gallons per day per filter. So now we need to figure out the number of filters needed for this rated capacity and flow per filter. So the number of filters is going to equal rated capacity over flow per filter. So that is going to equal our 12 million gallons per day given in the problem over 0.922 million gallons per day per filter. Doing the math works out to just about exactly 13 filters. All right, do we have any questions on any of the problems we've gone through today? Anything you'd like me to go back and review over one more time?
All right, Davis, not seeing any comments in the Q&A. You covered a lot of information. Great job on working through these problem sets.